This is the Innova Engineering Torque and Drag tutorial. In this video, we're going to run through a torque and drag calculation from start to finish. So we will cover the inputs required for setting up the calculation, running the calculation itself, and then we'll take a look at the results, charts, and reports. This video assumes that the viewer has already watched the hydraulics video. In the hydraulics video, I go into much more detail on the various ways that you can construct your drawstring, your well geometry, your fluids properties, and your surveys. So that you don't have to sit and listen to all of that again, I will not go into as much detail in this video. If you need a refresher on the drawstring tab and the surveys tab, I recommend that you re-watch the first half of the hydraulics video. I will, however, be discussing the inputs in the drawstring and surveys tab that are important for running an accurate torque and drag calculation. In this example, I will once again be rebuilding example project 3 from the examples folder. So if you need to check any of the inputs that I enter into this video, you can do so by going to File and Open, navigate to your Engineering Install folder, go to the Example Projects folder and just open up Example Project 3. Before I start, I just want to go over some of the other resources that we have available. So there's always the help file. Just go to Help and then Help. If you get stuck on what a particular input field does or a particular option, the best place to look is usually the help file. In the documentation folder, so if we go to Help and Open Documentation folder, we have some extra guides in here, specifically the Torque and Drag Quick Start Guide, which performs the same function as this tutorial video. It will run you through a torque and drag calculation from start to finish. We also have some extra guides on interpreting some of the torque and drag results charts. So we've got the apparent weight on bits chart, the casing wear chart, and the drill pipe fatigue chart. And then lastly, we also have our online tutorial videos. At this stage, the most useful videos will probably be the ones in the Innova Engineering Getting Started playlist. But we have a number of videos on specific sections of the software, which are also very useful. The first thing I'm going to do for this tutorial is create a new project. So I'm going to go up to File and New. I'll give my project a name. And a description. And then I'm going to set my units. So I can go through all of my units individually and set the ones that I want. Or I can go down here and I can pick one of the preset unit sets. I'm going to pick API units, which will set all of my individual units so that they match with the standard API units. And then I'm just going to tweak it by setting my length measurement from feet to US feet. And then I'm going to save my project by going to File, Save As. I'm just going to save it onto my desktop. So the first input that I'm going to start entering is my drill string. So I could enter my drill string manually, or I could enter it via the component catalog. But in this video, what I'm going to do is export my drill string from example project 3 and then import it into this project. So first I'm going to open up example project 3. And then I'm going to go to File and Export BHA. And I'm just going to save it on my desktop. And then I'm going to reopen my torque and drag project. And then I'm going to go to File and Import BHA and import the .bha file that I exported from my example project. And that will have imported in all of my drill string components, and it will have already filled in all of the component details down the bottom. You'll also notice that the length for my drill pipe that goes back up to surface has been set to 24,608 feet so that it stretches from the top of the reamer all the way back up to surface. This isn't necessary, this is just so that it looks good on the report. If I want to, I could just put in one joint of drill pipe as my last item, and then when I run the torque and drag calculation, the program will just automatically repeat this last component, my drill pipe, over and over again until it's long enough to reach back up to surface. So I can actually leave my drill pipe as just one joint length and it won't affect the calculation at all. In the main drill string table, all of these inputs are important for the torque and drag calculation. So the length of your components is important, apart from the very last one. The weight of your components is important. If you're entering a component that has a tool joint OD and ID, that needs to be entered as well. And the OD and the ID of your components also needs to be entered. The program uses the OD and the ID to work out the wall thickness of your components, which then affects how they respond to tension and compression and torque. So it's important to get these correct, and it's important to make sure that you don't put an ID of 0 in for any of these components. Even in components which normally don't give an ID in BHA sheets, like say motors, it's not acceptable to just put 0 in here. That will stop you from getting a realistic result. For stabilizers or components that include stabilizer sleeves, the OD and the ID that you put into the main drill string table is the OD and the ID of the stabilizer body, and then in the component details is where you enter the details for your stabilizer blades. In the component details for each of these components, there are quite a few fields to fill in. Some of these are required for the torque and drag calculation, and some of them are not. The best place to check which details you need to enter is in the help file. So if you go to help and then help, so we'll bring up the help file, and then you want to look at Appendix E. This lists all of the component details that are available for each component type, and it'll also tell you which calculations they're used in. So some will be used for just hydraulics, some will be used for just torque and drag, some will be used for both. If a component detail field says that it's used in engineering, then it's used in multiple calculations, including torque and drag and hydraulics. I'll now run through the main component details that are important for the torque and drag calculation. So in the bit, you've got the TFA, and the TFA is important in the torque and drag calculation because the pressure drop below the bit is used for buoyancy and buckling calculations. So to edit my TFA, I just want to select the TFA field and then click on this little grey box here. This will open up my jet details window. So I can manually enter my jets, so I can enter in the size of my jets and the quantity, or I can click on this fixed TFA button, which will then allow me to just type in any TFA that I want. So once you've entered in your details, you just hit OK, and that will set the TFA for your bit. Likewise, in RSS type components, MWD type components, and motor type components, you have a field for the pressure drop as the mud passes through that component. That's also required for torque and drag, so that needs to be entered. And in motor type components, there's also a differential pressure field, which will need to fill in as well if you have a motor in your BHA. For stabilizer type components, or components that can have stabilizer sleeves on them, so that's your RSS, your MWD, and your motor, you have fields in your component details that let you fill in information for your stabilizer blades. So you have your stabilizer OD, so that is the total OD of your stabilizer with its blades. Got stabilizer blade length, got stabilizer distance from the bottom, so that's the distance from the pin end of your stabilizer, and then you've got stabilizer blade width. Those all need to be entered when running a torque and drag or hydraulics calculation. And then lastly, in your drill pipe, you have your drill pipe material and your drill pipe class. So for your material, you can pick between steel and aluminium. The default is steel, but if you're using aluminium drill pipe, you can select it from this drop-down box, and that will change the Young's modulus of your drill pipe, which is used in buckling calculations. And then in the class, you have a choice between new, premium, premium plus, class 1 and class 2. Changing the class modifies the wall thickness, and you can see by how much by going to Tools and then selecting Pipe Class Editor. This will bring up the Pipe Class Editor, and then you can see the default values for the wall thickness of each class, and you can also edit them here if you need to. So a new class pipe will keep 100% of its wall thickness, and then a Premium Plus will keep 90%, and so on and so forth as you go down to lower classes of pipe. You'll see for all the components in the component details, there's a field for tensile yield and torsional yield, and for drill pipe, there's also a burst and collapse field. These values can be displayed on results charts, but they're not actually used in any calculations. So they're good to fill in if you have them, but if you don't have this information, then don't worry about it. Now that we've filled in our drill string, we can move up to the well geometry section. And in this section, we're going to define the diameter of the wellbore from surface down to the bottom of the section that we're investigating. You only need to worry about the parts of the wellbore that your drill string and your drilling fluid are actually exposed to. So in this example, I've got a 9 5/8 casing that runs from surface down to the top of the open hole section. I could have other casings in there as well that were set during previous hole sections, but because they are cemented behind the 9 5/8 casing, they don't make up any part of the diameter of the wellbore, so we don't have to worry about them. So I'm just going to insert my 9 5/8 casing for my top section. So I pick my type from my type drop-down box, I select casing, and I'm going to put in the measured depth of the casing shoe. And if we had some surveys set up already, then the program would automatically calculate your TVD for you. And I put in my casing ID and OD. Next, I fill in my open hole section. And in this example, we have two open hole sections. We have a small section of 8 7/8 open hole section before we get to the 8.5 inch section that we are drilling currently. So my 8 7/8 section of open hole runs down to this measured depth, and then I fill in either my ID or my OD, and the program will automatically copy that across to the other cell because it's an open hole section. And then lastly, I fill in my 8.5 inch open hole section, and the measured depth that I enter is the TD depth of my 8.5 inch section. So it's the depth after this section has been drilled. There we go, that's our well geometry entered. So now we can move down to our fluid properties section, which is where we define our drilling fluid. For torque and drag, we only need to worry about the mud weight, the PV and the YP values of our mud. I'm going to enter my mud weight, my PV and my YP values. Down in the bottom half of the fluid properties section, we have the cuttings details and the additional fluids. The cuttings details defines the size of the cuttings as you're drilling. This information is using the hydraulics calculation for calculating hole cleaning. We don't use it in torque and drag, so it's okay just to leave them as the default values. In the additional fluids section, you can enter information for additional fluids like pills or sweeps. You can enter in the volume of the additional fluid and its density. And when you run the calculation, the program takes any additional fluids you have here and your mud weight and combines them to create a new drilling fluid in the wellbore with an average of the mud weight between the mud weight entered here and your additional fluids. I'm not going to enter anything into these additional fluids. I'm just going to leave it disabled. So now that we've finished with the drill string tab, we can move on to the surveys tab. In the hydraulics video, I go into much more detail into the different ways that you can enter information into the surveys tab. But in this example, I'm going to jump ahead to importing my surveys using the import survey function in the file menu. In my hydraulics example, I imported my surveys into my well plan table, but in this example, I'm going to import them into my actual surveys table. This is just to demonstrate that the actual surveys and the well plan tables work in exactly the same way. The reason that you can choose between one or the other in engineering is just so that you can store one of each in the same engineering project file. So I'm going to go to File and Import Survey. Now I have a choice of different file formats that I can use. So I've got a tab delimited or a space delimited text file, a comma delimited CSV file, an Excel file, a navigator short color correction TXT file or LAS file. My import file in this case is a tab delimited text file, which I have saved on my desktop. So I just select the file, click Open, and this will bring up my import survey window. So you can see my survey data in the table in the bottom. And then at the top, I'm going to pick the start row and the end row for my data. So I want my data to start at row 2 so that it cuts off this header information that's in my table. So I set it to row 2. And then my end row is 269. And then below that, I choose which column in my table represents my measure depth, my inclination, and my azimuth. So above each column, I have a drop-down box, and I can choose what type of data it is. In this example, my column's already correctly lined up, so I can just hit Import. I'll get a warning saying this will overwrite any existing data that I have in my surveys table. That's fine, just hit OK. And those are my surveys pulled in. You'll see in this survey listing there are a few sections which are perfectly straight. So we've got a perfectly straight section just here. We've got a completely vertical section just here. And then as we get into our lateral section, you can see this is perfectly straight as well, maintaining the same inclination and azimuth for quite a long way. This is not a good representation of a real-life well, and straight sections, and especially completely vertical sections, can cause the program to output unrealistic results. So to get around this problem, we're going to add some tortuosity to our surveys. And to do that, we just want to click on this tortuosity button down at the bottom of the window. This will open up our tortuosity window, and we can turn on tortuosity by clicking on Apply. And what tortuosity does is it adds or subtracts a tiny amount of inclination or azimuth to your surveys. So it doesn't affect the trajectory of your well, but it gets rid of any completely straight parts. So you have an option of the type of tortuosity you can apply. You can apply sinusoidal tortuosity or random tortuosity. Random tortuosity will just apply the additions and the subtractions randomly, whereas sinusoidal will apply them so that they increase and decrease following a sine wave function. So I'll set my tortuosity to random. And then we have the period length of the tortuosity. So the tortuosity is applied in a repeating pattern, and you can just set the length of this pattern before it repeats using this option here. I'm just going to leave it as the default 25 feet. And then if you check this depth range checkbox, then you can set a start depth and an end depth for your tortuosity. So if you only wanted to apply it across a certain range, you can do that here. I'm just going to leave it as the entire length of my surveys, and I just hit OK to apply my tortuosity. So you won't see your tortuosity applied in the surveys that you've entered here. In order to see it, you need to click on this Calculated Survey Data button down at the bottom. But before we do that, we need to go into the Engineering Parameters tab quickly and just check that Engineering is actually going to use the actual surveys for the torque and drag calculation, and we do that in this survey selection section in the middle. So I'm just going to pick actual surveys for my drop-down box and go back to my surveys tab. And now I can click on Calculated Survey Data. So engineering doesn't actually use the surveys that you enter into your actual surveys or your well plan surveys box for the calculation. what it does is it takes those surveys and any tortuosity that you've applied, and it creates this interpolated survey listing. And if you scroll down to an area that was previously completely smooth, you'll see that there's been some tortuosity applied to it. So this area here, which was completely vertical, has now got a little bit of inclination and azimuth added or subtracted to it. This raw survey data section and this survey correction section is just used for raw survey correction, so you don't need to worry about these if you're just running a torque and drag or hydraulics calculation. And this vertical section just here lets you change the azimuth of your vertical section and can shift the origin of your vertical section north or south and east or west. And this just affects how your vertical section is calculated in your survey table, and also how your section view plot is displayed. And you can access the section view plots as well as your plan view plot and your 3D view plot in the plots menu at the top of your screen. So we've got the section view, the plan view, and the 3D view. So now that we've input our surveys, we can move on to the Engineering Parameters tab. This is where we enter the last few setup parameters needed to run the calculation. And it's split into 5 sections. Over on the right hand side, we've got the hydraulics results section and the driller's hook load and torque data section. This hook load and torque data section will populate automatically with results when we run the torque and drag calculation. Then on the left, we've got a hydraulic setup section, a survey selection section, and a torque and drag setup section. When we were setting up the hydraulics, we were able to completely ignore the torque and drag section. But when we're setting up the torque and drag, there is one part of the hydraulics setup section that we need to worry about, and that is the flow rates section just here. So in order to run the torque and drag calculation, we need to enter one flow rate. If you have manual flow increment checked off for your flow rates, then the flow rate that you enter into the middle field of this table is the flow rate that the torque and drag calculation will use. If you have manual flow increment turned on, then the flow rate that you have entered in the first line of your table is the flow rate that the torque and drag calculation will use. So I will just put in my flow rate there like that. Moving down, we have the survey selection section. So this is where you choose which of your surveys that you entered into your surveys tab you want to use for the calculation. So if you did have information entered into both your actual surveys table and your well plan table, then this is where you choose which one you actually want to use for the calculation. So you have the choice between the actual surveys or the well plan table, and then there's a composite listing choice, which just adds these two tables together. I'm going to pick the actual surveys, and then I can move down to my torque and drag setup parameters. So first we have the calculation depth, and this is the depth that the calculation is going to run at, and is also the reference depth for all of your snapshot graphs and tables. And I'll explain what a snapshot graph is when we go over all of the torque and drag results. Usually this will be the deepest depth of your bit, which in most cases is going to be the bottom of your whole section. So I could enter this depth manually, or I can use this last survey depth button or last geo depth button to pull in my calculation depth from some of my other inputs. So last survey depth, if I click this button, will set my calculation depth to my lowest survey in my actual surveys, and last geo depth will set my calculation depth to the bottom of my rod geometry, which I set up in the drill string tab. So if I click on last survey depth, this will set my calculation depth to the deepest depth that I have in my surveys. In the RPM box, you set the RPM of your drill string during whatever activity you're investigating. So if you were drilling, this would be the RPM that you're drilling at. If you were reaming, then this would be your reaming RPM. I'm going to set my RPM to 100. Then the next option down is my pipe speed. This is the up and down movement speed of your pipe. It affects your reaming hook loads and your reaming torques, and also your pickup weights if you have viscous drag turned on in your options. I'm going to set this to 30 feet per minute. Weight on bit, rotate is my weight on bit while I'm rotating. I'm going to set this to 14,000 pounds. And you can see here, there's also weight on bit for sliding. If you leave this option unchecked, then it'll just automatically copy whatever you put in your rotate weight on bit. But if you want to, you can toggle this on, and then you can set a separate weight on bit for your sliding. Next is the overpull. And so this is just the overpull applied to your drawstring assembly when you're pulling out of hole. I'm going to leave this as 0 for this example. So block weight is the weight of your traveling block in your derrick. I'm going to set this as 38. And if you want to, you can toggle on these two options here. And this will let you set separate block weights for when you're picking up and when you're slacking off. Optimized standoff is when you're looking at casing standoff. The casing standoff is outside of the scope of the basic torque and drag tutorial and has its own video, so I'm not going to cover anything related to casing standoff in this video. Next we have bit torque, and this is an estimation of the torque generated by the bit. If you leave the option unchecked, it'll calculate automatically based on your bit OD, which you set here in your drawstring, and from the weight on bit that you entered. If you want to, you can toggle this option on and manually enter an estimation for the bit torque. Next is side force units. So when we run the torque and drag calculation, we will get a result for side force. And this is where you can set the units that this is expressed in. So it's expressed in 1,000 pound-feet per unit of length that you enter here. If you're using side force to predict casing wear, then you should set this length to the length of a tool joint. So I am going to set this to the length of one tool joint, which is about roughly 30 feet. Next is the casing wear factor. So when you run the torque and drag calculation, it'll output a result for estimated casing wear. And here you can set the casing wear factor, which just modifies the result. A casing wear factor of 1 doesn't change anything, but a casing wear factor of 1.5 would increase the amount of wear by 50%, and 0.5 would halve it. In our help file, under the Engineering Parameters tab and Torque and Drag Parameters section, we do have a table which will help you estimate what the casing wear factor should be. I'm just going to leave this as the default of 1. And then we have the ROP. So this is your rate of penetration while you're drilling. So for this example, I'm going to put in an ROP of 150 US feet per hour. And then lastly, we have our friction factors table. The friction factor is a value that represents all of the sources of friction in your system. And it should be a value between 0 and 1, with 0 being no friction and 1 being a lot of friction. And it's affected by things like the roughness of your casing and your wellbore, cuttings build-up, dogleg, pipe stiffness, and the mud that you're using, to name a few sources. So you enter friction factor values for your cased hole and for your open hole sections. And there's 2 ways of filling in this table. If you enter in a friction factor in the middle field, then the program will automatically generate some other friction factors above and below it. Alternatively, you can select manual friction factor increment by clicking on this checkbox, and then you can fill in the tables with as many friction factors as you want. So I'm going to leave my manual friction factor increment turned on, and then I'm going to fill in these tables. Okay, so that is all of our engineering parameters set up for the torque and drag. We've got our surveys entered, and we've got our drill string, our well geometry, and our fluid properties set up. So now all we need to do before we run the calculation is check our options. You can access your options via the options menu at the top of your window. All the options do is tweak how the torque and drag calculation runs. There are some options here which affect both hydraulics and torque and drag. There are some that just affect torque and drag. I'm going to run through just some of the main ones. So first we've got include tool joints and include stabilizers or centralizers. So these are on by default, but if you toggle these off, they just completely remove the effects of tool joints or stabilizers in your drill string from the calculation. We've got these survey calculation methods. So this is how the program interpolates between survey points in your survey tab. Normally, you would just leave it as the default minimum curvature. And then we've got the torque and drag model options. So these are options that are specific to the torque and drag model. First is viscous drag. This refers to the drag caused by pulling the string through the mud, and it affects pickup weights. Buckling friction. If this is turned on and there is buckling in your drill string, then this will add additional friction as if the pipe was being pushed up against the side of the well. This only applies to slack-off weights. Contact surface correction. If you turn this on, then tubulars with a larger OD will cause more friction. This is because they have more surface area in contact with the side of the wellbore. Calculate casing wear. If you turn this off, then the casing wear results will not be calculated. Buckling lines. You can choose between sliding or rotary. This sets what type of buckling line is displayed on your tension on and off bottom snapshot charts. So if you were mostly interested in buckling while sliding, you would select sliding. And if you were mostly interested in buckling while rotating, you'd select rotary. Seeing as how we have an RSS in our BHA, we're more interested in buckling while rotating. So I'm going to change this option to rotary. For the buckling model, you can choose between a conservative or a standard model, and this affects how your helical buckling limit is calculated. So engineering calculates two types of buckling, sinusoidal buckling and helical buckling. The helical buckling limit is just the sinusoidal limit multiplied by a certain amount. In the conservative model, it's multiplied by 1.4, which is the default. And then in the standard model, it's the sinusoidal limit multiplied by 2.1. So under the conservative model, your helical buckling limit is going to be smaller. I'm going to pick the standard model. Include friction reduction subs. So in drill pipe and in heavyweight drill pipe in the component details, there is an option to add friction reduction amount. If you have a friction reduction sub added onto your drill pipe or your heavyweight drill pipe, and this option just lets you toggle on and off whether or not that friction reduction is applied. Include overpull in stretch calculations. So if you turn this on, then the overpull that you entered into your torque and drag section in the engineering parameters tab will be taken into consideration when pipe stretch is being calculated. By default, this is left as no. Outer stream properties. This is where you input some parameters for expandable liners. As expandable liners are outside of the scope of this video, I'm going to skip over this option. Next is the step interval. The step interval determines the depth interval between the calculation points when the calculation is running. When your units is meters, this is by default every 10 meters. And when your unit is feet or US feet, then this interval is every 30 feet. So you can increase the resolution of your torque and drag results by reducing this number, but that will increase the load on your computer when the calculation runs, so it can increase the time the calculation takes. And likewise, if the calculation is taking a very long time, you can increase this interval, which will speed up the calculation, but will also reduce the resolution of your results. I'm going to leave it as the default 30 feet. So the next one down is air drilling options. So if you were drilling with air instead of mud, you would want to open up this option and enable air drilling by clicking on this checkbox here. And then you would enter in the standpipe pressure expected in your wellbore. And this will allow the program to calculate the extra string weight caused by drilling with air instead of with mud. As we're drilling with regular mud, I'm just going to leave that disabled. Then fluid level. If your fluid level isn't surface, then you can enter the measured depth of where the top of your fluid level is in this box. And then between surface and whatever measured depth you enter here, the program will take this into account and will make sure that no buoyancy from the mud is applied in this region. And then lastly, we have include bowstring force. So when this option is turned on, if you're modeling a casing run and that casing has got bowstring centralizers included in the drill string, then by having this option on, the extra friction caused by these bowstring centralizers pressing against the side of the wellbore will be included in your torque and drag calculations. If you need a reminder on how any of those options work, then the best place to look is the help file. Let's go to help and help. Pull up your help file, and then the options menu is under menus, options menu. You've got the general options menu, and you've got the torque and drag model options as well. And likewise, if you need a reminder for any of your torque and drag parameters, then the help file is the best place to look as well. So now that we've got our options set and all of our tabs filled in, we can now run the calculation. So we do that by going up to Calculate and selecting Torque and Drag. And when it's finished, you should see this message saying Torque and Drag calculation complete. And you can see that your hook load and torque data results have filled in. So on the left, you have a table of hook load results for different bit depths. You've got a rotating off bottom and a rotating on bottom results column. And then you've got columns for pickup and slack off at different combinations of cased hole and open hole friction factors. And then your last column, you've got a minimum weight to helical buckle. So this is the minimum weight on bit required to get the drill string to buckle at the assigned bit depth while tripping in. And then on the right, we have some torque results. So again, you've got your bit depth down the left, and then in each column, you've got some off bottom and on bottom torques at different combinations of cased and open hole friction factors. So if you want to, you can quickly export these tables out. If you left click in the top left corner of your table, press Ctrl+C to copy, and then bring up something like a Excel spreadsheet, and then just press Ctrl+V to paste. You can paste your tables into an Excel spreadsheet that way. But there are also ways to output these tables via your torque and drag results, which you can access from the torque and drag results menu at the top. So in your torque and drag results menu, you have a selection of charts at the top, and then you have some data tables which contain the data required for plotting the charts at the top. You've got some extra survey and stress data, and then you've got a torque and drag summary, a standoff summary, and a dogleg chart. So we'll take a look at the torque and drag results charts. These are split into two different categories, much like the hydraulics results charts. The first category are just normal drilling charts, and then the second category are snapshot charts. The difference between these two is how they handle depth. So in a normal chart, such as the hook load chart, your depth value on your y-axis represents the depth of the bit. But in a snapshot chart, such as this off-bottom tensions chart, your bit or your casing shoe stays at the calculation depth that you set in your engineering parameters. And in the title of a snapshot chart, it'll say what your calculation depth is to remind you where your bit or your casing shoe is. And then your depth measurement on your y-axis, instead of telling you where your bit or your casing shoe is, it represents a point in the wellbore or in the drill string. So for example, in this chart, our bit stays down at the bottom of the wellbore, and then a depth of 10,000 feet tells us what's going on at 10,000 feet in the wellbore. So on this chart, it's telling us what's going on in the drill pipe at 10,000 feet. I'm now going to run through most of these drilling charts and snapshot charts and briefly explain how you interpret each of them. I'm not going to go over how you customize the charts. I'm going to leave that for the charts and reports tutorial video. So first is the hook loads drilling chart. The hook loads chart will tell you the predicted hook load depending on the depth of your bit and the type of activity that you're doing. So we've got lines for rotating off bottom, rotating on bottom, picking up, slacking off, and sliding. And for picking up, slacking off, and sliding, we've got multiple lines for the different combinations of friction factors that we entered into our friction factors table. So to make things a bit easier to see, I'm going to clear out everything apart from the middle friction factor. So this blue line will give you the predicted hook load when picking up. This green line is rotating off bottom. This light blue line is the hook load when you're rotating on bottom. This red line is when you're slacking off. And this orange line is when you're sliding. And the sliding line also depends on the weight on bit that you entered in your engineering parameters tab. And then this pink line is the minimum weight to helical buckling line. So if any of the other lines cross below this helical buckling line, it means that you're going to experience buckling somewhere in the string. The hook load chart can tell you the string depth and the hook load that buckling is going to occur at, but it can't tell you where in the string that buckling is going to occur. To make the helical buckling line a bit easier to see, you can toggle this button on, which will shade in below your helical buckling line. Next is the torques chart. The torque chart will give you a predicted value for your torque based on your bit depth and your case and open hole friction factors. So the blue lines represent off-bottom torque at different friction factors, and the red lines represent on-bottom torque at different friction factors. Next is the reaming hook loads chart. The reaming hook loads chart works the same as the hook loads chart, but it displays results for when you're reaming in and reaming out. And in the title of the chart, you can see the speed that you're rotating at and the speed that the pipe is moving up and down. And these are set in the engineering parameters in the RPM field and the pipe speed field. Next, you have the reaming torques chart. And again, this is just the same as the torques chart, but instead of showing results for rotating on bottom or rotating off bottom, we've now got results for reaming torque while picking up in the blue and reaming torque while slacking off in red. Next, we have the pipe stretch chart. This predicts the total amount of stretch that you expect to see in your drill string when you're picking up. So on the y-axis, you've got the depth of your drill string when you pick up, and then depending on your friction factor, the chart will tell you the pipe stretch in inches. Next, we have the pipe twist chart. This chart predicts the number of complete revolutions that the rotary table has to be turned in order to turn the bit. So it represents the number of wraps in the drill pipe when it is rotating off bottom. And again, you've got different results for different friction factors. Next is the apparent weight on bit. In the title of the apparent weight on bit chart, you can see your desired weight on bit, and this is what we entered into the weight on bit parameter in the engineering parameters tab. And depending on the depth of your bit and your friction factor, this chart will tell you what weight on bit you need to see at surface in order to achieve the desired weight on bit. So in this example, my desired weight on bit is 14,000 pounds. So if my friction factors were 0.2 for cased hole and 0.2 for open hole, and my bit was down at 20,000 feet, then I would trace over to my 0.2 and 0.2 line, and then I can see that the weight on bit that I actually need to see at surface is about 21,500 pounds. Next is the apparent overpull chart. Now, if you haven't entered any overpull into your engineering parameters, this will just appear as a straight line. So I'm going to put in some overpull and then rerun the calculation. When you do have an overpull entered, this works exactly the same way as the apparent weight on bit chart. So I've got my desired overpull up here in my title, and then I choose my bit depth and my desired friction factors, and the chart will tell me how much overpull I need to see at surface in order to achieve my desired overpull. Next, we've got the snapshot charts, starting with the off-bottom tensions chart. As I said earlier, in a snapshot chart, your bit or your casing shoe, if you are modeling casing, stays down at your calculation depth, which is stated in the title of the chart. And then the depth on the y-axis represents a point in the drill string. In our example, this will be almost all drill pipe. In fact, we can toggle on the BHA component depths using this button. And you can see that the BHA is just this tiny sliver at the bottom of the well. If we zoom in, we can see all of our BHA components at the bottom of the well. These red, green and blue lines show the tension at that point in the drill string during different activities and different friction factors. So these blue lines represent picking up, the red lines represent slacking off, and then this green line in the middle represents rotating off bottom. If the tension value at that point is positive, that means that the component is in tension, and if the tension value is negative, then that means the component is in compression. In the off-bottoms tension chart, we have two lines for buckling. The light blue line represents sine buckling, and the pink line represents helical buckling. And I can toggle the shading for these on and off using this button here. So if any line passes below the sine buckling line, then that means it's in sinusoidal buckling. And if it passes below the helical buckling line, that means it's in helical buckling. You can choose in the options menu whether or not these buckling lines are for rotating or for sliding. And as we're using an RSS in this example, I set the buckling lines to rotating in the options. We also have this line here, which represents string tension with overpull. So this is picking up plus the overpull that we set in the engineering parameters. And then lastly, we've got this tensile limit line. So if you do have tensile limit information for your components, you can enter that into your component details in the drill string tab, and then you can display the tensile limits on your off-bottom and on-bottom tension charts. And then you can see if any of the drill string components go over that limit. Next, we have the on-bottom tensions chart. This works in the same way as the off-bottom tensions chart, but this time we are on bottom, so we have a weight on bit applied. And instead of slacking off, the red lines represent sliding. So on the off-bottom and on-bottom tensions chart, you can identify where in your drill string you are getting any buckling. When you have the on-bottom or off-bottom tension charts open, you also have access to the buckling analyzer, which you can open by clicking on this button here. The buckling analyzer will give you a column for any of the activities which are experiencing buckling, and then will give you some extra information. The helical buckle length and sine buckle length give you the total length of drill string that is under helical or sine buckling. Then you've got the helical buckling index and the sine buckling index. These are unitless values which give an indication of how severe the buckling is. So the higher the value, the worse the buckling. Then you just got a depth value, which gives you the calculation depth, and the weight on bit, which gives you the weight on bit that you entered in the engineering parameters. Next is the torque snapshot chart. In the torque snapshot chart, your bit or casing shoe is down to your calculation depth. And then by picking your depth off the y-axis, you can find the torque in the drill string at that point. We've got two sets of lines. So the blue lines represent torque when off bottom, and the red lines represent the torque when you're on bottom. Next is the side force snapshot chart. This chart shows you the side forces acting on the drill string during different activities and for different friction factors. So you've got side forces for pickup, slack off, and rotating. And the side forces in this chart are measured in 1,000 pounds per 30 US feet. And we set the 30 US feet part of the unit in our engineering parameters. Next is the apparent weight on bit. So the apparent weight on bit snapshot chart works a lot like the apparent weight on bit driller's chart, but in the driller's chart, we kept our desired weight on bit static and varied the depth. And in the snapshot chart, we keep the depth static and then we vary our actual weight on bit. So when the bit is at your calculation depth, you can pick your desired actual weight on bit from the y-axis, then read across to your chosen line for the friction factor, and then you can read down and find the apparent weight on bit that you want to see at surface in order to achieve this desired actual weight on bit. And you can do this vice versa as well. So if you see 50,000 pounds apparent weight on bit up at surface, you can use this chart to work out what actual weight on bit you're getting down at the bottom of the hole. Next is the apparent overpull. This works in exactly the same way. So when the bit is down at our calculation depth, you can convert between the apparent overpull that you're seeing at surface to the actual overpull that you're getting down at your calculation depth. Next, we have the casing wear chart. The casing wear chart gives a prediction of the total amount of wear at each point in the casing when the assembly is at the calculation depth. The amount of wear depends on your wear factor and the RPM that you entered into the engineering parameters. And the period of time that the wear is measured over depends on your ROP and the length of your open hole section in your weld geometry. You've got casing wear lines for two different activities. You've got casing wear while rotating and casing wear while slacking off. And you can see from the units of my x-axis that there's a very, very small amount of wear happening over the course of this example. Next is the drill pipe fatigue chart. The drill string fatigue chart displays the actual dogleg and the critical rotating dogleg at every point in the drill string for when your drill bit is at the calculation depth. The critical dogleg line is generated based on the free rotating weight of the assembly. If at any point the actual dogleg is larger than the critical rotating dogleg, then fatigue failure is a potential issue. Next is the pressure data chart. In the pressure data chart, your bit is down at the calculation depth, and your flow rate is the flow rate that you entered into the hydraulics parameters. And then the chart will give you the internal and external pressure at each point in the string for that flow rate. Underneath the Drilling Charts and the Snapshot Charts menus, we have the Drilling Data and Snapshot Data menus. These give you the same results as the chart, but in a table format. So for example, I open up the hook loads drilling data. This will open a table that contains all of the data points that were plotted on my hook loads chart. And if I want to, I can export this table by going to File and Export. And then I can save my table either as a text file or an Excel file. Next, we have survey data. This can only be opened when you have the Surveys tab open, and it simply opens the calculated survey data window again. Next is stress data. So clicking on this will open up the stress data table. This is a snapshot table, so your bit or your casing shoe will stay down at your calculation depth, and then the depth value in the depth column represents a position in your drill string, and the component in the component column will tell you which component that depth is referencing. So for most of this drill string, it's drill pipe, but we've got our BHA down at the bottom. And in the other columns, we have results for various different types of stress that component is experiencing at that depth. The results depend on the operation that you're looking at, and you can choose which operation that is using this drop-down box at the top. So for example, we can change to picking up at a cased hole friction factor of 0.2 and an open hole friction factor of 0.2. I can view my results for this activity in my table, and I can export the data by clicking on this Export Data button here. And that will let me save this table that I'm looking at as either a text file or an Excel file. And then lastly, I can view the results for this operation on a chart by selecting View Chart up here. We have the Dogleg Chart, and this simply opens up a chart that displays the dogleg severity for the surveys that you've entered into your Survey tab. And then lastly, we have the torque and drag summary. The torque and drag summary performs the same function as the hydraulic summary. It's a way to generate a report for your results quickly and easily. So at the top of the summary, we have all of our inputs that we entered into the drill string tab and the engineering parameters tab. If I skip over this table quickly, you can see we also have a summary of the drill string. So this is just what we entered into our drill string tab for our BHA. And then we have the hook load chart and the torque chart. And then in the middle, we have this torque and drag summary table. In the header of the torque and drag summary table, we have these two results for weight on bit to sinusoidally buckle and weight on bit to a helical buckle. And what these results are telling us is that when our bit is down at the calculation depth, this is the minimum weight on bit required to get sinusoidal and helical buckling when rotating on bottom. And it also tells us where in the drill string this sinusoidal buckling and helical buckling will occur. And then in the table below, we have a summary of results for all of the different operations while your bit is down at your calculation depth. So we've got the surface weight, which is the hook load, the surface torque, the pipe stretch, the pipe wraps, whether or not there's any buckling present in the drill string, and it will tell you if this is helical or sinusoidal buckling. And then you've got your friction factors and your RPM value. And then you can see the different operations that it lists. So we've got rotating off bottom, rotating on bottom, tripping in, tripping out, sliding, reaming in and reaming out. And for operations where it applies, you've got a result for each of your different friction factors. So the torque and drag summary lets you print a report with just one click, but you can't customize it. If you want to customize what goes into your report, you need to go to File, and print reports, and this will bring up the reports manager. I'm going to cover all of the different options that are available in the reports manager in the charts and reports video, but for now I'm just going to give an example of how I can customize my talk and drag report. So I can choose whether or not I want to output my report in PDF or Excel format. I'll stick with PDF. I can customize a few things like whether or not I want a cover page or a header and a footer. And then I can come down to my talk and drag tab, and I can pick which results I want to go into my report. So I'm going to create a talk and drag summary, but I'm also going to add in my surveys and all the charts that are available. And then I just click on this printer button to print my report. And there we go, we've got our talk and drag summary. We've got all of our charts. And then we've got a table of our surveys. That concludes the talk and drag tutorial video. We'll now move on to the questions and answers section. After each question, try pausing the video and seeing if you can answer the question yourself before getting the answer. First question, what hydraulics properties are needed for torque and drag calculations? And the answer is, in the component details you need the bit TFA, any pressure drops and motor differential pressure, and then in the engineering parameters you need a flow rate. Question 2, is it acceptable to leave the ID or weight of a component blank if I don't know it? And the answer is no, the program reads this as 0. You need to make sure that you've entered accurate OD, ID and weight values for all of your components in your drill string to make sure that you get an accurate torque and drag result. Question 3, what component details affect the stiffness of my drill pipe? And the answer is the pipe class, which affects the wall thickness of the pipe, and the material, which affects the Young's modulus. Question 4, what depth is my bit or casing shoe at in a snapshot chart? And the answer is, in a snapshot chart, your bit depth or casing shoe depth, if you're modeling casing, is always at the calculation depth that you entered in your torque and drag engineering parameters. And lastly, where should I check if I can't remember what an input parameter or a component detail does? The answer is, the best place to look is in the help file. For input parameters, you want to look in the appropriate section or chapter, and for your component details, you want to look in Appendix E. Now we can move on to the exercise. This is going to be very similar to the hydraulics tutorial video exercise. You're going to create a torque and drag calculation from scratch and then run it and then take a look at the results. For your data, you can use your own data or you can copy the data from one of the example projects. So start by creating a brand new engineering project, set up your units, then create a drill string by inserting components from the component catalog. Alternatively, you can export a BHA for one of the example projects and import it into yours. Make sure that you fill in all of the important component details for your drill string. Then create a well geometry and fill in your fluids properties. Then enter some surveys into the survey tab. If you need to, you can copy surveys directly from one of the example projects. And if it's required, Don't forget to use the Tortuosity tool to add some tortuosity to your surveys. Enter your torque and drag parameters into the Engineering Parameters tab. Set up your options in the Options menu and then run the calculation. Take a look at some of the charts in the Torque and Drag Results menu and then print off the torque and drag summary. If you become stuck at any point, refer back to the video for a refresher. Thanks for watching. If you need to get in contact with us, you can do so via the emails that are on the screen now.